Okay, part 11 of Applied Maths for Game Development, and we're starting to get into the good stuff now, 2D geometry, and that's based on the Cartesian system invented by René Descartes. Sorry, I nearly pronounced it wrong there. This specifies points on a plane defined by horizontal and vertical positions, also called x and y axes, and it starts from point 0, 0, which is the origin. So if we specify point 5, 3, it takes us up to there. On the screen though, on a computer, they're basically Cartesian, but because computers draw from the first pixel downwards, we kind of sort of invert the y-axis. So it goes from top to bottom instead of bottom upwards. And there's nothing wrong with that, it's just a different frame of reference. So if we had 50, 30, that would be where the first pixel of our hero is drawn there. And that's the code you would write for or something like that. There's different systems out there though. I'm just going to mention one just to illustrate. This one may be useful to you at some point. So polar coordinates are where you have, instead of x and y, you use r and theta, that Greek symbol there. This specifies a point on the same plane, but it does it by taking a line on the x-axis, rotating it theta degrees, and then moving n units along that. Sometimes it uses that little angle symbol. For example, you would write something like p equals 5, angle 45. So 45 degrees from the x-axis, and then move 5 units along that line. Here's a visual aid. So here's the x-axis. Theta is 26 degrees, so take that line there, rotate it 26 degrees, you get this orange line there. And if you take r, 6.7, and travel 6.7 units along that line, that's where you get to. So instead of saying 6, 5, you could easily specify, or just as easily specify 6.7, 26 degrees, or 0.46 radians, which is the same measurement in a different, the same amount in a different measurement. We'll see what radians are a bit later. But polar is a different way of specifying it. It may sound like a more difficult way to do it, but it actually has some benefits, otherwise you wouldn't bother. So to convert between these two systems, you can use Pythagoras' theorem. The r of a polar coordinate is equal to the Pythagoras' theorem of the equivalent x and y values. So square root of x squared plus y squared gives you r. Theta, the angle, needs to use a function called the inverse tangent, which we won't see until a bit later, but it's called atan. So if you take y over x, do the arctangent or atan function on it, that will give you theta. As long as x is not 0, if x is 0, by the way, then that you know that the line's pointing straight up or down. So you can treat that as a special case. So to get Cartesian coordinates from a polar point, that's the other way around, and these are quite famous and very important equations. The x and y values would be x equals r cos theta and y equals r sine theta, related to SOHCAHTOA, if you know of that. We'll definitely see that when we look at trigonometry in more detail later on. But that's how to convert between polar and Cartesian. So moving on, geometry, we tend to use Euclidean geometry, named after Euclid, of course. And in this kind of geometry, a point is a unique location specified by coordinates that cannot be broken down into smaller geometric objects. So it's not a solid thing, you can't split it up. It's just sort of think of it as an infinitely small location, although in reality, in programming, we're typically using it to talk about a point on the screen, which is a pixel, which does have a certain size. A vertex is a point where two lines meet. So most importantly, if you're making a geometric object like a square or a triangle, then each of these would be a corner of that shape. Next, you can make lines, rays, and line segments. How long is a line? Well, it turns out in math, lines are infinite. So a line is actually an equation, and linear equations have no endpoint. You can use it to specify any position anywhere infinitely. But if you do put an endpoint on, then that line becomes a ray because it stops there. Or to think of it another way, it starts there and continues infinitely in the other direction. So it's like shining a ray of light from that source. But if you've got two endpoints, then what you end up with is a line segment that joins 2 points together. So the equation of a line is one of the most common algebraic constructs. It takes this form, y equals mx plus c. You probably heard me mention it earlier. This tells us that for any point on a line, you can take the x coordinate and work out the y coordinate. So x is the known variable, y is the unknown variable, and we've got an m and a c value which we need to look at shortly. So the gradient or slope of a line is how quickly it rises. If you've got a linear equation, the gradient is the m value. So since y equals mx plus c, if you take the change in y and the change in x, if you happen to know how quickly it moves along the x and y axis, you can rearrange that formula. Sorry, I thought I might have had that in there, but you can rearrange that formula. So what you do is get the change in y divided by the change in x. So the change in y is called a rise because it's sort of the thing rises up the y-axis, and the change in x is called a run. Divide them together, you'll get m, or the slope or gradient. The x-intercept is where a line crosses the x-axis, and the y-intercept is where the line crosses the y-axis. And if you've got a linear equation, c happens to be the y-intercept. It's just that simple. Here's an example. This line crosses the y-axis at 0, 1, so therefore c equals 1, that's the y-intercept. The line goes from 0, 1 to 1, 3. So there's one change in x, that's your run, and there's two change in y, it goes from 1 to 3, so that's your rise. So for every 1 it runs along, it rises 2. 2 over 1 is of course 2, so m is 2, you've got a slope of 2, a gradient of 2, and therefore, so c is 1 and m is 2, y equals mx plus c, 2x plus 1 in other words. That's the formula of that line there. Now, two lines are parallel if they have the same angle from the x-axis. Parallel lines never meet, always remain the same distance apart. The symbol for that is 2 bars. And also, I don't know if I've mentioned it already, but a line typically has that symbol above it. So the line AB and line CD are parallel. That's how you would see it written. Two parallel lines have the same m value. Now for intersecting lines, these have a different angle from the x-axis, and because lines are infinite and they have a different angle from the x-axis, they must intersect at exactly one point. At that point, the x and y values satisfy the equations of both lines. So you've got y equals mx plus c for one and y equals mx plus c for the other, and at the point where they intersect, the y and x values satisfy both those equations. So because of that, you can do simultaneous equations to find that point, but I'm not going to do that right now. That's not the point of this video. Next, you've got perpendicular lines. These are lines which are at right angles to each other. They always intersect, and the symbol there for two lines being perpendicular is that sort of upside down T. If in perpendicular lines, the slope m of one slope is the inverse negative of the slope m of the second line. It's probably best to look at the example to see that. The m of one is -2, and the m of the other is a half. So what we do is, if you had to work one of them out from the other, you would just take the m value, put it in the inverse of a fraction, and stick a minus sign in front. So this one here has a slope of -2. It's going 2 downwards. If you take -2 and put it in here, that'd be 1 over -2, and then stick a minus sign in front. Those two minus signs will cancel out. You'll get 1 over 2. So the slope of the perpendicular line is 1 over 2, or a half, in other words. And of course that works in reverse as well. You may need to find the midpoint of a line segment. So obviously this only works if you've got 2 points. Can't find the middle of something that's infinite. So all you do is simply average the x and y values. So in this example, the x value 3.5 plus 0.5 is 4. Half that to get the average, and it's 2 for the x. The y values are 3 and 1, add them, you get 4, and average that, you get 2 again. So the midpoint is 2, 2. Okay, angles. If you have razor line segments that start at the same vertex, then you can measure the difference in the direction they're pointing. So in other words, technically, angles only apply to razor line segments, not actual lines themselves. So this is called an angle from the Latin word angulus. But although it doesn't apply to lines, really, you can kind of make it work. If you have a line, or a rare segment that doesn't start at the same vertex, then you can just find the vertex where they cross over, pick a direction from there, and just use that part of the line. So effectively, you can do it. And that's usually what people mean if they say the angle between two lines. So if you have only one line, you can still calculate an angle. It would be the reference angle, and that's the angle between that line and the x-axis heading rightwards. Here's some terms for angles. If it's less than 90 degrees, we call it acute, an acute angle. Oh, that's radians as well. So radians is calculated based on pi. We'll see that in detail later on, but 90 degrees is equivalent to pi over 2. So if it's less than pi over 2 radians, it's acute. 90 degrees is called a right angle. If it's between 90 and 180 degrees, it's called obtuse angle. Exactly 180 is a straight line. If it's more than 180 degrees, we call that a reflex angle, and they're important for collision detection. Reflex angles mean you can't really do collision detection very easily. 270 degrees is a 3/4 circle, and 360 degrees is full circle, and that's 2 pi. Because of 2 pi, some people think we should use tau, which is 2 pi, but let's not confuse things. Okay, next up, circles and arcs. Technically, a circle is a continuous set of all points. So it's an infinite set of points along the edge or the outside of the circle. And they're all equally distant from some kind of center point. Circle comes from the Greek kirkos, sorry for pronunciation again, which means ring. The general form of the equation of a circle is x minus a all squared plus y minus b all squared is equal to r squared. A and B are the centers. If you see that written as x plus a and y plus b, then you would need to say the point minus a minus b is the center. It's the same way of doing it, just flipping where the minus signs are. So basically those two terms, negate them and you get the center. R is the radius of the circle. Oh, sorry, for that example there. So 2, 2, 2, that's the center. And the radius is 1. So here's some key concepts to do with circles and arcs. The point, whichever location on the circle is equally distant from, is called the center. That's the middle of the circle. The radius is the distance from the center to the edge, any point on the edge. So this one here has a radius of 1. There's also a diameter, which is from one edge to the other, passing through the center. And it's always going to be double the radius. The circumference is the length of the line all the way around the edge from one point all the way around back to the point it started at. The area is the space inside the edge. An arc is just a portion of the edge, just that sort of blue bit there. But a sector is what you get if you take an arc and then use it to slice up the circle from the center. So that's a sector. Now, a tangent is a line that touches the circle exactly once and passes straight by. A chord touches it twice, passes in and goes back out again. And segments are the shapes that get created when you cut a circle using a chord. So pi is one of the most important numbers in all of mathematics, and there's its definition: the ratio of a circle's circumference to its diameter. So in other words, pi is circumference divided by diameter. And of course diameter is 2r, so pi equals circumference divided by 2r. So if we rearrange that, circumference, put it on the other side, then we get circumference equals 2 pi r, one of the most famous formulas. And I'll just throw in the other one, famous one to do with pi, which is the area of a circle is pi r squared. Right, moving on, looking at polygons now. So polygon comes from the Greek meaning many corners. It's a solid shape made up of lines connecting 3 or more vertices. So if you've got 3 vertices, we call that a triangle, or trigon if you want to be fancy about it. And inside a triangle, the 3 angles must add up to 180 degrees, or pi in radians. You can have a quadrilateral, also called a tetragon. That's 4 sides. That's squares, rectangles, parallelograms, etc. And the interior angles add up to 360 degrees. If you've got 5 sides, we call it a pentagon, 540 degrees inside. 6 sides a hexagon, 720 degrees. 7 sides a heptagon, 8 sides octagon. You've got nonagon, decagon, etc. after that. but at some point it gets silly. Polygons can be regular, which means every line at the edge is the same size, and all of the angles inside are the same. So for example, a square, each angle inside that is 90 degrees. But you can also have irregular polygons where this isn't the case. You can have convex polygons. None of the interior angles are reflex, so it doesn't kind of bow back outwards. And concave, so one or more of them are reflex angles. So it sort of caves in a bit, as I guess that's how I remember it anyway. A simple polygon, none of the lines cross over, but in a complex polygon, the lines cross over each other, and that can result in this sort of hourglass shape. It can even result in some part inside the polygon being bounded by the polygon, but not part of it, if you get what I mean. So the first polygon type is a triangle. In some algebras there are smaller ones, but it doesn't really make sense in Euclidean geometry to have a polygon with 2 or 1 vertices. So a triangle is where we start. A three-sided polygon, and it's used loads. An absolute ton of triangles are used in computing because you can make any other polygon out of them. And triangles can be right angled, which means one of the angles inside is 90 degrees. They can be equilateral, which means all the angles are 60 degrees. Or they can be isosceles, which means all the angles are different. Oh no, sorry, I beg your pardon. Isosceles means two of the angles are the same. And scalene is where none of them are the same. You can look at the perimeter of a triangle, which is roughly equivalent to the circumference of a circle. It's the length of the edge, the outside of the triangle. It's called the perimeter. You can also find the area of a triangle. To do that, make sure it's placed horizontally, rotate it if you have to. And then a line that's horizontal is called a base. Multiply that by half of its height. So there's the formula there. Quadrilaterals. A quad or tetragon is a four-sided polygon. And here's a few. A parallelogram, where it's made up of two pairs of equal length, which are both parallel, and the angles are two pairs of equal angles. You can have a rhombus, which is a quad that has all the same properties, but is also a regular polygon. So there's kind of diamond shaped. A rectangle is where a quad which has four right angles, but the opposite lines are of equal length, but not all four of them are the same length. And a square is regular polygon, four right angles, all sides being equal length. That'll do for now.